तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we looked at the statement of the compensation theorem and worked out a simple example to illustrate the application of the compensation theorem. We promised ourselves at that time that we will look at a justification or the proof of the compensation theorem in the next lecture, and that's what we are going to do presently. We have a network comprising various linear elements. A typical element, two terminal element, is indicated here, carrying a voltage Vk and current Ik. We have a number of independent sources. A representative source, kth source, is indicated here. Number of current sources, kth current source, is indicated here. The voltage across in the current in the voltage source is indicated by ISK. We don't want to use the capital letter because that has been reserved for this, and the voltage across the current source is given small Vsk, and there is an impedance Z in the network which is carrying a current I. Now the question which we would like to ask is what are the changes produced in the network when Z is changed to Z plus delta Z. So this is the original network and this is the altered network. In the altered network we have the impedance has changed Z plus delta Z, otherwise the parameters are the same. However, the variables in the network undergo changes. The voltage or the independent voltage source cannot change because that is an independent voltage source, but the current changes from ISK to delta ISK. The voltage across the current source changes from VSK to VSK plus delta VSK, and the general voltage of an element changes from Vk to Vk plus delta Vk, and the current in this changes from Ik to delta Ik. All these variables with the original network and here are functions of S. We take them to be Laplace transformed variables, and the impedances are functions of S, generalized impedance functions. So we would like to analyze this to find out the alterations in the various variables in the network. To do that, since the current I plus delta I is flowing through Z plus delta Z, by substitution theorem we can replace this impedance by a voltage source which has got the strength. The voltage developed across this is I plus delta I times Z plus delta Z. So this is the voltage of this voltage source which can be used in the place of this Z plus delta Z, and the rest of the network will not see any change. That is the principle of the substitution theorem. Now this composite voltage source can be split up in this fashion, which the purpose for that will be evident later, but let us say I plus delta I times Z plus delta Z is broken up into three sources. Their sum will add up to this: IZ, I times Z, that is one source; delta I times Z plus delta Z, that is one source; and I times delta Z, that is the third source. So sum of these three sources will add up to this value. So instead of this impedance, we can replace the series combination of these three sources and say that the conditions in the network will not change. Now, so we have, as far as this altered network is concerned, we have the various voltage sources, various current sources, and these three independent voltage sources standing for the impedance Z plus delta Z. Now to find out the conditions in this network under these excitations, I use the principle of superposition. So I take all the voltage sources and current sources were originally existing plus this single source. So VSK, ISK and this IZ, that is, I consider the effect of all those sources once, and when you do that, these two sources must be short circuited, therefore that is they are not present here. And then I would like to find out the effect of these two sources alone, keeping the other sources deactivated. Therefore I write delta I times z plus delta z and I times delta z, these are the two sources that are active, and all the other sources are deactivated. Therefore this voltage source is short circuited, this current source is open circuited, and similarly all other current sources and all other voltage sources. Now let us look at this network. In this network we have essentially the same conditions as in the original network, because in the original network if we have Iz, I can certainly replace this by a voltage source I times Z, and the network will not change, will not, all the parameters, all the variables in the network will remain the same. So in the original network, instead of the impedance Z carrying a current I could as well have replaced it by a voltage source Iz. Therefore that is exactly what we have here. Therefore the variables inside here for this network is the same as the original network. So this is the original network, original conditions, because this is the same as the original condition. That means this Iz is equivalent to simply an impedance Z, and the current here will remain as I, this is Vk, and the current here is Ik, this is Isk, this will be Vsk, and this will be Isk. So this is the, all the conditions in this network are the original conditions. Consequently the sum of the conditions here and the conditions here must be the conditions in the altered network. Therefore this network will tell us the changes that are brought about in the various voltages and currents. So this we can call this incremental network. And in the altered network the total current here is I plus delta I, this is I, therefore this has got to be delta I by the principle of superposition, because this is a linear network, the sum of these quantities must be equal to the quantity here, therefore if this is I, this must be delta I. And this voltage, this is Vk and this is Vk plus delta Vk, therefore this must be delta Vk, and the current here likewise is delta I. And this in the shorted lead here, this is Isk, this is Isk plus delta Isk, therefore this must be delta Isk, and the voltage here must be delta Vsk. So if you solve this network, you will be able to find out all the quantities, all the changes that are brought about as a result of the change in impedance. But we do not know what delta I is. How do we find that out? I mean that is exactly what we want. So you do not know the strength of this voltage source, but then you observe a delta I passing through an impedance Z plus delta Z produces just that much voltage. So again, using the substitution theorem in a reverse manner, you can replace this by means of an impedance which is Z plus delta Z. So if you replace this voltage source by an impedance Z plus delta Z, delta I flowing through that will produce that much voltage source. So we use the substitution theorem in reverse fashion and say replace this portion by an impedance Z plus delta Z for this. So delta I flowing through that will produce that much voltage. So as far as the incremental network is concerned, all we have to do is deactivate all the original independent sources, introduce a voltage source I plus delta I times delta Z in series with the altered impedance, and put the altered impedance in position Z plus delta Z and this source working into this network will establish currents and voltages in this network, which are the increments that are caused as a result of the change in impedance. That means the incremental network, so we will write here. So the incremental network will be simply one in which all the voltage sources are short circuited, all the current sources are open circuited, and you have the altered impedance Z plus delta Z, and you have a source, voltage source, which is the change in impedance delta Z multiplied by the current which was originally flowing in that element. So whatever this voltage source produces, those will be the changes in the network, delta Bk, delta Ik. So this is what we said is a statement of the compensation theorem in the last lecture, and this is the proof for that. A few comments on this. First of all, delta Z is only change, need not be small. We have nowhere used the fact that delta Z is a small increment. It could be quite large. It could be 100%, 200%, no problem at all. Now secondly, if you compare this statement of the theorem with the Thevenin's theorem, if you replace the original network by Thevenin's theorem and then change the Z from Z to delta Z, you can calculate the increments that are produced in the load impedance only. Whereas here you find out the changes in all the elements, whereas Thevenin's theorem can be used to compute the increments in the load impedance as a result of a change. Here we can find the increments in the entire network. So this is an advantage. Now what we have to see, another thing is there should not be any coupling. There should not be any coupling between delta Z and other elements in the network. Because when you change those coupling elements are destroyed, therefore we should not have a mutual coupling or coupling through control sources between the delta Z and the other elements of the network. The fourth point, if the original impedance Z has initial conditions, the equivalent initial condition sources remain the same. That is, if originally we had in this impedance some inductance carrying a current or a capacitance carrying a voltage, and you had replaced this by initial sources here, they continue to be the same in this network. There is no problem about that. However, if delta Z has some initial conditions, what we mean is an inductor carrying a current or a capacitor having a voltage, then the equivalent initial condition sources must be incorporated. That is, in addition to delta Z times I, we must also have an additional source, usually a voltage source in series with that, to represent the initial conditions that are present in delta Z. So this is something which we have to pay attention to. Apart from this, you must also keep in mind the polarity of this incremental network. This is the incremental network. Original current was in this direction. So delta Z times I, if delta Z is positive, then the current must be in the source should be such as to drive a current in the opposite direction. This is something which we already mentioned. So let us work out an example to illustrate this idea. We have here a Wheatstone bridge network which is used to test a resistor Rx. So these are the values of the resistors in the fixed arms, and the resistance of the galvanometer is also 600 ohms. Now the nominal value of the resistance Rx is 600 ohms. So if this is 600 ohms, the bridge is balanced, 600, 600, 1200, 600, galvanometer current is 0. So the galvanometer current is 0 when the Rx happens to be 600 ohms. So nominal value of Rx equals 600 ohms. However, this bridge is used to test a whole lot of resistors, and the tolerance allowed for the resistor is plus or minus 5%. So we would like to test a whole batch of resistors, and as you put each resistor, we should like to define the range of current which is acceptable if the Rx is to be within the tolerance. That means if the resistance can change from 570 to 630. So depending upon the value of the resistance, the galvanometer current, center zero galvanometer current will not be here, it will deviate one way or the other, and we would like to set up what is the lower limit of the current and what is the upper limit of the current if the resistance is to be within the tolerance limits. So that is the problem. So Rx can change, Rx can lie between 570 ohms and 630 ohms. And we would like to find out the galvanometer current for that. Now if Rx was 600 ohms, the galvanometer current is 0. So if from 600 ohms it deviates to 630 ohms, what is the galvanometer current we would like to establish? Similarly, if from 600 ohms it changes to 570 ohms, what is the galvanometer current? That is what we should establish. Since the original galvanometer current Ig is 0, what we can do is we can you can use the compensation theorem conveniently, and when Rx changes from 600 to 630, what is the incremental current that is produced in the galvanometer would be indeed the total current, because the original current was 0. So using compensation theorem, we will set up the incremental network for when Rx goes to 630 ohms. So you have the original network 1200, 1200, and the galvanometer current, galvanometer is 600 ohms. This is 1200, this is 600 ohms, and the source resistance is 1200 ohms, and the independent source is deactivated. And here in the galvanometer this is 1200, and in the galvanometer branch you have the altered resistance which is 630 ohms, and you have a DC source which is equal to the change in resistance, which is 30 times the original current. The original current here can be computed, and it will be equal to 4 milliamperes. So the current here is 4 milliamperes in the original network. So 30 into 4 millivolts. So with this voltage, what is the current in the galvanometer? That is what you should calculate. It can be shown, you can use this network and then calculate the current in the galvanometer, and it can be shown to be 39.2 microamperes. In a similar fashion, you also calculate the current in the galvanometer when the resistance changes to 570 ohms, and now the change in the resistance is minus 30 ohms, and the original current is 4 milliamperes. That means the voltage will be 120 millivolts in this direction, because delta Z is negative, therefore it should be in the opposite direction. So with this you can calculate the current, and this can be shown to be equal to 40.8 microamperes. So we can now say that the galvanometer current must be from 30.8 on 39.2 in one direction to 40.8 microamperes in the other direction. As long as the current lies within that margin, the resistance is between 570 to 630 ohms. If it exceeds that margin on either side, then the resistance goes outside the tolerance limits. So this is an example of illustration of use of compensation theorem in situations like this. Let's work out a second example. This is a slightly more complicated example where Laplace transform method is used. Let us see what it is. You have a 12 volt source, DC source, operating in a circuit which has a 1 Henry inductor, and then the switch is closed at t equals 0, connecting a 4 ohm resistor. Find I of t for t greater than 0. So that is a straightforward problem. We can do it using the loop current method of analysis, Thevenin's equivalent and so on, but we would like to use compensation theorem for that. What we propose to do is, we would like to solve a resistive network removing this inductance. So then it will be pure resistance. We solve that, and we consider that as the original network. Now we introduce this inductance here as the additional impedance introduced into this circuit, and then use the compensation theorem to find out the effect that are produced. So we can say that we have the original network which has a purely resistive affair, two ohms, 4 ohms, and then another 4 ohms, and then this is 12 volts. I can we'll use it in Laplace transform domain, so I will put this as 12 by S. And in this network, if the switch is closed at t equals 0, what are the various currents that are produced? So there will be a current here, and this current will be here. So the current here will be, of course, this I will call this IL, so that we will say the load current IL. IL of S, and I will call this IX of S. Okay. So this is the original network. We can solve for that quite straightforward fashion. The load current IL of S will turn out to be 1.5 amperes. Therefore 1.5 by S is that current, because after all in the DC network 4 ohms in parallel with the 2 ohms, 2 ohms in series with 2 ohms is 4 ohms. Therefore the current here is 3 amperes. Therefore 1.5 flows here, 1.5 amperes flows here. So Ix of S is also 1.5 by S. This is the original network. Now we want to introduce an inductance in this circuit and find out what are the conditions, what are the alterations that are produced here. So in the incremental network, we have this 4 ohms, and an inductance is introduced of this impedance function is S, and this original source is deactivated, that is it is replaced by a short circuit, and here again the switch is closed, of course, at t equals 0, and then you have 4, this is also 2, this is 4, this is 4. Now, the change in the impedance is S, and the original current in the inductance branch is 1.5 S. So, the compensation voltage that you get here is 1.5 by S, that is the original current, multiplied by the change in impedance, which is S. This is the compensating voltage. Right. But that is not all, because this inductance here in the network has also an initial current. Before the switch was closed, the inductance is carrying a current, and what is the current? 12 volts divided by, when the switch is open here, 12 volts drives a current of 2 amperes through these 2 ohms and 4 ohms in series. Therefore, a 2 ampere current was flowing through that. Therefore, we have 2 times inductance is 1. So, that voltage is also should be there. This is the initial current source. So, the source which represents the voltage source which represents the initial current in the inductor, that also must be put in place. So, this is the incremental network, and you can use this incremental network to calculate the current here when the switch is closed, and that current plus this current will be the total current. Therefore, you have this current can be shown to be IL dash S. In this you can calculate this, and it can be shown to be, or we can say delta IL, maybe that is better. We can use, after all this is IL, we can call it delta IL of S. You can analyze this network and calculate delta IL of S. It will be minus 0.5 divided by 3S plus 16, or it can be shown that delta IL of T is minus 1/6 e to the power of minus 16 T by 3. So, IL of T here is 1.5. Therefore, the total current in this altered network, original network, is IL will be 1.5 minus 1/6 e to the power of minus 16 T by 3. So, this is the answer for this problem. So, this example illustrates an interesting application of compensation theorem, where we have the reactive element completely removed in the original network. You introduce the reactive element as an additional impedance and calculate the increment that are produced within this network. We shall now discuss a new network theorem which has the name Elegance theorem. B.D.H. Telegan was a research scientist with the Philips laboratories in Netherlands, and he proposed the theorem around 1952 or so, and it did not receive the attention worldwide at that time. 15-20 years later, it was received worldwide attention because of its generality and the fact that a whole lot of network theorems can be derived from Elegance theorem. You would find in most textbooks written in circuit theory written prior to 1969 or thereabouts very rarely contain a reference to Elegance theorem, but nowadays it would be difficult for us to spot a textbook, a modern textbook, which does not contain a reference to Elegance theorem. That means its importance has been boosted up. This is as a result of the discovery that Elegance theorem can be employed in studies of sensitivities of networks and similar other situations to a great advantage. In fact, the generality of Elegance theorem gives it a unique place in circuit theory. It has all on the same footing as Kirchhoff's laws. That means it is as fundamental to network theory as Kirchhoff's laws in a sense. Let us see what Elegance theorem is, statement of the Elegance theorem is, and we would like to illustrate this by an example and use this for one or two applications to derive other network theorems. So, we will take up first of all the statement of Elegance theorem. let us consider two networks of identical topology. So we have a network like this, another which has got the same geometry, same manner of connection of elements, but these two networks are not the same. They have, however, the same geometry, the same method of interconnection of the various elements. We will call this network A, call this network B. And we have not made any specific commitment about the nature of the elements. The elements here quite arbitrary, the elements here also quite arbitrary, and this element need not be the same as this element. They may be voltage sources, current sources, whatever element we have. Now suppose you take the kth element here, that means each element, kth element here is a one-to-one correspondence with the kth element here, because the geometry is the same. Suppose we say the voltage across this is Vka in the A network, and the current through that is Ika. We will say small Vka, small Ika. Similarly here, let us say this is Vkb and the current here is Ikb, that is the kth element, and like that we have a whole lot of elements. Now suppose I take this voltage of the kth element here, multiply by the current in the kth element here, and sum them up over all elements. I will get Vka multiplied by Ikb summed on k over all elements in the network. Now let me do the other reverse operation. Take the voltage of the kth element in the Bth network, multiply by the current in the kth element in the A network. Then I will get Vkb times Ika. Elegance theorem says both these are equal. This is the equality. You take the kth element here, voltage of the kth element here, multiply with the current here, sum up over all possible elements in the network. Similarly, take the current voltage in the kth element here, multiply by the current in the kth element in the A network. This is the summation that you get, and both these are equal. And it does not make any difference what the elements are. The elements could be quite arbitrary. So this is the statement of elegance theorem. All we demand is that the two networks have identical geometry. We call that identical topology. That means there must be one-to-one correspondence between the two, an element here and other element there, from the point of view of interconnection with the other elements. Now proof of this can be given in this manner. Suppose in the A network you have the kth element like this, and let us say the nodes of the kth element are m and n. So you have the kth element, this is the kth element, you have the voltage Vmn in the A network, and let us take B network. By the way, elegance theorem says not only these two are equal, but they are also equal to 0. They are also equal to 0. You take the voltage of the kth element, multiply with the current in the kth element in the B branch, sum them up, it will be 0. Similarly, if you do the reverse operations, that means both these expressions are equal to 0. So we would like to show this product, the sum of these products is equal to 0. That is what we are going to establish. So in the B network also we have a kth element which is connected between the nodes m and n, and the current here is Ikb. That is the current in this Ikb. Now let me multiply this. This is Vmn A, of course, in the A network. Let me multiply this voltage by this current. So Vmn A multiplied by Ikb. That is what we want to take the product, and then multiply, sum them up over all possible elements. So all elements k. So we do that for all elements k. We want to show that this is going to be equal to 0. Now we can write this as, after all, the voltage between nodes m and n can be written as Vm A minus Vn A in the th network multiplied by IKB summation, all elements k. This node, the voltage across the kth element Vmn, the drop from m to n, I am writing the node voltage of m with minus the node voltage of n with reference to some datum node in this network. Now this can further be written as all node pairs Mn, node pairs Mn, Vm A times IKB minus Vn A times IKB. So after all, I have expanded that and I have put this Vm A times IKB minus Vn A times IKB. Now if you look at this, what we are really doing is, we are taking the node voltage Vm A, multiplying by the current that passes through IKB, leaving this node m in the network B. So if you do this for all possible nodes, then what you will get is, suppose you take an rth node R, so we will say all nodes R. So let us take an rth node, some node. When you have an rth node here somewhere, and then you have various elements connected here. So if you carry this summation over all possible node pairs, this rth node figures whenever there is a current involved in these three elements. And what we have seen is, when the current IKB leaves the node m, we have given it a positive sign, and the current enters the node n, we have got a negative sign here. So if you consider take stock of such products summed up over all possible nodes R, then we have VR figures wherever there is a current, wherever we take a branch which is incident at R is concerned, and we are going to multiply VR by the current to that branch with a positive sign when the current leaves that node R, and with a negative sign when the current enters the node R. So if you look at this carefully, we can write all nodes R times RA, of course, A, algebraic sum of currents leaving node R in network B. So these are the currents in the network B. So you take the node voltage R in the network A, multiply by the algebraic sum of currents leaving node R in the network B, and by Kirchhoff's current law this is going to be 0. Therefore this will be VRA times 0, and so the whole thing is 0. So that is the principle of elegance theorem. What it says is, you take the voltage here, multiply with the current in the corresponding branch, sum up over all branches, that is going to be 0. And likewise, if you take the voltages here, multiply by the currents here, and sum up over all branches, that likewise is going to be 0. So this is the principle of elegance theorem. In this, one thing we should note is, we have made use of Kirchhoff's current law and voltage law in deriving elegance theorem. We have already made use of Kirchhoff's current law here. We see unless this algebraic sum of currents leaving node R in the network B is 0, we can't get this result. We also made use of Kirchhoff's voltage law, whether we have recognized this or not. You observe that I said Vmn A, the voltage between this across this element K is Vmn A, we said is equal to node voltage of M with reference to datum minus the node voltage of N with reference to the datum. Such an identification of node voltages is possible only if you have Kirchhoff's voltage law valid, because when you go around a loop between two nodes, if you get different voltages as you take two different paths, then Kirchhoff's voltage law is not satisfied. So we will have, when we say a particular voltage, node voltage is a definite value, then we assume that Kirchhoff's voltage law is valid. So that is very important, and that is what we have assumed. So in a sense, Kirchhoff's current law plus Kirchhoff's voltage law have been used to deduce elegance theorem. TT means elegance theorem. In fact, it can be shown that any two will lead to the third. We can also show, I don't do it here, but Kirchhoff's current law plus elegance theorem will imply Kirchhoff's voltage law. Kirchhoff's voltage law plus elegance theorem implies current law. So these three are intertwined in such a way that any two will lead to the third one. A few comments before we take up some examples. Few comments on elegance theorem. Comments or amplifications of this. It is possible that we can identify A and B. A and B may be the same network. That means we are applying this elegance theorem to the same network, currents in the one network, the currents in the same network, and Vk and Ik measured at the same instant. So if you take the currents and voltages to be at the same instant, elegance theorem says Vkt times Ikt summed up over all k. After all, there is no point in now saying A and B because it is the same network. Vkt times Ikt is 0. This is a statement of conservation of power in the network. If you take the instantaneous power associated with each element, add them up over all elements, that is going to be 0. This is something which we already know. This is a consequence of elegance theorem. This is a conservation of power. It is a statement of conservation of power, which of course is not very surprising. Suppose you have A and B same network, Vk and Ik measured at different instants, measured at different times. So that means if you take Vk at t1 and multiply by Ik at t2, then also it is 0 on some k. This is not something which is immediately evident. It is not a manifestation of conservation of power. You can take the currents in these voltages in a network at a time t1, multiply the currents at another time t2, still their product is 0. This is surprising. Third thing, A and B are different networks. Are different networks, but identical topology, but with identical topology. Then only this theorem will work. Then Vk A t1 multiplied by Ikb in general t2 sum, that is also 0. This is something surprising. In fact, we can even generalize this. Vk's can be instantaneous values, phasors, or Laplace transforms. So can VKAs, I will say, so can IKBs. So that means you can have this, all the VKs can be either instantaneous values, can be phasors, can be Laplace transforms, so can IKs be. And it is not necessary that if you choose the set of VKs as Laplace transforms, IKs also should be Laplace transforms. The surprising thing is I can multiply the Laplace transform of voltages multiply by the instantaneous values of currents in the second network. They have no physical meaning, the product, but still this is 0. It means as long as the set of voltages that you take satisfy Kirchhoff's voltage law, as long as the set of currents you take satisfy Kirchhoff's current law, and you know phasors satisfy Kirchhoff's current law, the Laplace transforms satisfy Kirchhoff's current law, instantaneous values satisfy Kirchhoff's current law. So as long as the whole set of VK satisfy Kirchhoff's voltage law, the whole set of currents satisfy Kirchhoff's current law, then you can use this theorem, and there is no compunction for that for us that if VKs are Laplace transforms, IKs should likewise be. IKs could be instantaneous values. As a matter of fact, any set of variables which satisfy voltage constraints, Kirchhoff's voltage law constraints and current law constraints can be used for this particular application of elegance theorem. And another important feature is the network elements are arbitrary. They can be linear or non-linear, active or passive. Reciprocal or non-reciprocal, whatever it is, absolutely no restriction on the network elements. The only requirement is Kirchhoff's current law and Kirchhoff's voltage law must be valid, and the two networks have identical geometry, so that you can put one element in one network in one-to-one correspondence with the other element. So this is a very powerful theorem, and as I said, when it was proposed by Telegan around 1950, it did not receive the attention that was due. It was only later on that people found out the generality of this, and there is a nice book written by Penfield, Spence and Winker. Around 1970, which is titled the elegance theorem and its applications. It shows how the elegance theorem can be employed to prove several other network theorems, and so that is a very general kind of network theorem, and it's a very important one. So in this lecture we had first of all started with the proof of the compensation theorem, how an impedance in a network changes from Z to Z plus delta Z, how the increments brought out in the network can be computed by analyzing the network with a single source which is equal to delta Z times I. So if the delta Z carries initial currents and initial energies, therefore you have to another source also, and but all the other independent sources inside the network are deactivated. We worked out one or two examples to see the advantage of application of compensation theorem in solution of networks. Then we went to the discussion of elegance theorem. We mentioned elegance theorem applies in its generality to two networks which have identical geometry or topology as they are called. That means the manner of interconnection of elements is identical, so that one element could be placed into one-to-one correspondence with another element in the second network. Elegance theorem says that if you take the voltage of an element in one network, multiply by the current in the other network, and do this for all networks and add them up, it will turn out to be 0, no matter what the network elements are, no matter what type of voltages, whether it is instantaneous values or Laplace transformed variables that you are talking about, no matter what the current variables are. The only requirement is individually the voltage variables must satisfy Kirchhoff's voltage law in every loop in one network, and the current variables must satisfy the Kirchhoff's current law in the network to which they relate. We will in the next lecture illustrate elegance theorem by means of an example, and then we will also use it to prove another network theorem, namely the reciprocity theorem applicable to two-port networks. That will be in the next lecture.